16. And the most important concept here it is that experimental work has shown that heat is another form of energy. Maybe like the old definition of heat has to do with like how many calories, and they thought that it is just a physical quantity or like something physical that is going to move from one object to another when they exchange the heat. But the new definition, and this is why it was really measured in calories. Now, James Joule used a device similar to this in the diagram to measure the mechanical equivalent of heat. Then, like, he was able to find what is really the mechanical equivalent of heat. And of course, like, he did a calculation here with like how much heat was provided and how we can make like that balance and what's the weight needed, and then he was able to to and also like the conservation of energy was used here to calculate what is the equivalent heat of the mechanical equivalent of heat. Now we can say that 1 calorie out of this it is 4.186 joules. Now, 1 kilocalorie is defined as the amount of heat needed to raise the temperature of 1 kilogram of water from 14.5 to 15.5 Celsius. Through experiments such as joules, it was possible to find the mechanical equivalent of 1 calorie to be 4.186 joules, because the mechanical, I will say the SI unit for energy, which is heat, is joules. Another unit that we are using here in the United States, it is the British Thermal Unit, BTU, and this is the energy required to heat 1 pound of water from 63 to 64 Fahrenheit. Now we are going to use for heat Q, okay? It is, I will say this is the amount of heat. We can calculate it in calories, but because our standard unit is joules, we are going to talk more about joules. And for me, I prefer always to have my calculations in joules. But if the question is not specifying a unit, then you can use whatever unit you like. Now let's talk about how materials are really responding to heat. Like, if I am transferring heat from one object to another, or I am taking off heat from something, or like the heat is moving out, like it was expelled, how this is gonna affect the temperature, okay? And the number that we are looking, or like the property that we are looking, it is called specific heat, and the heat capacity of an object is the amount of heat added to it divided by the rise in the temperature. This is here, we call that the heat capacity, okay? Heat capacity, it is just Q divided by delta T. But also, we can talk about another quantity I will, which is the specific heat in a little bit. Now, this is, of course, it has units of joule per Kelvin or joules per Celsius. A Q, it is positive if delta T is positive, that is, the heat is added to the system, and it is negative when the heat is expelled or removed from the system. Now, I can move to another physical quantity called specific heat capacity, and the heat capacity of an object depends on the mass. Okay, of course, it is different if you wanna warm 5 kilograms or you are going to warm 10 kilograms. Now, that quantity that it is related to the material, it is called specific heat, and it is defined as Q divided by M, over delta T. Most of my students, they're gonna call it MCAT, this equation. We put it usually like this. And then the specific heat can be calculated as the total heat added or removed divided by M times delta T. And when I am using the standard system, the SI unit for C, it is J per kilogram Kelvin, or J, which joules per kilogram Celsius. Here are some of the specific heats of various materials. And I will say, if we look at the number that is related to water, you're going to see that it is significantly high. If we look at metals, these numbers are really very low. This is the reason why metals are really like they need a very short time to reach a high temperature, and they will lose the heat fast. Like in winter, you are going to find that the knobs of doors, which are made of metals, they're gonna be like like maybe colder than the environment. Now, we are here in most of our questions, we are going to include like calculations of like maybe specific heat, final temperature. There are many things that we are going to use. Now, if we have what is called calorimeter that is lightweight, means that I will not include it in my calculation, and I will have that insulated flask containing water. When an object is put in it and the water come to thermal equilibrium, we can calculate Q, we can calculate C. Now, what's happening here is that this is the experiment that we do usually in the lab. Like here we have, this is water at room temperature. And then you're gonna record what is TI for water. Now, for my metal, usually I will use, of course, I will boil water to make it reach a temperature that it is closing to 90 or 100. Then my metal is going to be at a temperature which is TI metal, which is, I will say, approximately, usually we will make it reach maybe 90 or 100 degrees. Now, what's gonna happen after that, then this is my metal, whatever, it has, okay. This is before, and then after, I wrote before collision. This is before, and then after, what's gonna happen, you're going to add the object here. Here, if I neglected the calorimeter, I said the calorimeter is lightweight. Okay, then here I will say after. Now my object, the metal, is gonna lose heat, and the water is gonna gain the heat. Then I can say until they reach a temperature, I can call it T final. Now I can say that the Q lost by metal, and because it is lost, I will say, I will give it a negative plus the one that is for the water is going to be 0. Okay, then here what I can do is, okay, let me have it like this. Okay, Q metal plus QW should equal 0. Okay, why? Because, okay, what was lost by the metal is going to be gained by the water. Here, you're going to say M metal times C metal times delta T metal plus M water, seawater, delta T water should equal 0. From this equation, I will be able to calculate what is really the C for the metal. How much heat input is needed to raise the temperature of an empty 2 kilogram vat made of iron from 10 degrees to 90 degrees? What is the vat? What if the vat is filled with 20 kilograms of water? Now, the first one, it is just here, Q equals mc delta T. Then I have the mass of it, 20 kilograms. From the table, we have 450 for C, joules per kilogram Celsius, times the, if the difference in temperature, it is 90 minus 10, which is 80. Now, if it is filled with 20 kilograms of water, then I need to add both for the vat and also for the water, and I will add these two together. Just here, I want to bring to your attention that look here at this number. This is the heat that is needed to raise the temperature of, the water itself, and this is the container, which is iron. This is just because the specific heat of water is very large. All right. There are questions here where I will be asked to calculate what is really the final temperature. Then this question here, it is a final temperature question. If 200 centimeters cube of tea at 95 degrees Celsius is poured into a 150 gram glass cup initially at 25, what will be the common final temperature of the tea and cup when equilibrium is reached, assuming no heat flows to the surrounding? Of course, here I will say, since again they put into thermal contact, one of them is gonna lose, the other one, the warm one is gonna lose, and the cold one is gonna absorb. And then I can put the equations mc delta T for the tea equals mc delta T for the cup. Usually when we deal with I will say with liquids or like with water, what is given to us is given the volume. Then you need to find the mass, and the mass, it is the density multiplied by the volume here. Okay, then this is just to calculate what is the mass of the tea. And this says usually if the question is asking about coffee or tea, we know that we can use the one for water times the difference in temperature. We know the initial temperature is 95. The initial temperature was 95. Remember, this should be T minus 95 degrees Celsius. Okay, and we're gonna have a minus here. I prefer to have that solution like this, and then I'm gonna have a negative, then it's gonna be a plus. And this is the reason why it is inverted, because delta T, it is T minus 95, and it's gonna be negative. Okay, and doing the calculation, we will be able to calculate that temperature to be 86 degrees Celsius. Now, how heat can be transferred from one place to another? There are ideally three main methods of heat transfer: conduction, convection, and radiation. It depends on the medium, and conduction is the flow of heat directly through a physical material, which mainly we will talk about solids. Heat conduction can be visualized as occurring throughout molecular collisions. Then they're going to give the energy to each other after, the collision. Now, if I have a hotter surface and a cooler one, and I have here a cross-sectional area. Then I can say this is the heat conduction rate because it is divided by time. This is a constant called conductivity A. It is the cross-sectional area. T1 minus T2, it is the difference in temperature divided by L, which is the usually we are talking about insulating material, then this is the thickness of it. Experimentally, it is found that the amount of heat that flows through a rod increases proportionality to the cross-sectional area, increases proportionality to the temperature difference, and increases steadily with time, decreases with length of the rod. We can combine it this way, make it like this is another way of writing it. And here the constant K, we call it conductivity of the material. And really here in this table, some typical thermal conductivities are given. Now substances with high thermal conductivities are good conductors of heat. Those with low thermal conductivities are really good insulators. Here we want to try using it. A major source of heat loss from a house is through the windows. Calculate the rate of heat flow through a glass window that has these dimensions. This is the area and this is the thickness. If the temperature at the inner and outer surfaces are 15 degrees Celsius and 14 degrees Celsius. Then here just this is direct application, delta Q over delta T. It is K times A delta T over L. We can get that number for glass from here, from the equation. Put it, and then this is the dimensions of the window. This is the difference in temperature, and this is the thickness of the glass. Then it is 790 joules per second. Okay, here in the second one, I have a copper rod and an aluminum rod of the same length, and cross-sectional area are attached end to end, like we can see here. The copper end is placed in a furnace maintained at a constant temperature of 250 degrees Celsius. And the aluminum end, it is placed in an ice bath held at constant temperature of 0 degrees Celsius. Calculate the temperature at the point where the two rods are joined, like in the middle. Assume the temperature at the joint remains constant. Here, of course, if the temperature at the joint is gonna stay constant, this means that the heat flow in the two rods should stay the same. And then we will put the two equations together, and we know that here like the L is gonna cancel, the area is gonna cancel because they are the same. And then K copper is gonna be the temperature, the hot temperature minus the T in the middle equals K aluminum times T in the middle minus T cold, and we will be able to get that in T middle to be 1.6 into 2 degrees Celsius. The second method of conduction of heat, it is convection, and this is usually in fluids, in gases and liquids. And actually it is related to what is called currents that they're gonna form in the fluid because of the heat. Then this is here is gonna be, I will say, very warm because it is close to the stove. And then is gonna be low density. Then it's gonna move up, and then it will push the cold, and we will have that kind of currents. Now this is here to show you how really this is really related to the wind in land warmer than the water. This is during the day because of the sun, And then we will find that the air that is really next to the, or like close to the earth, is going to be warm, then it's going to go up and it's going to push the cold, and then we're going to have the sea breeze, and the opposite is going to happen at night. Now, the last method, it is radiation, and all objects give energy in the form of radiation, which is infrared. And of course, like I would say, at usual temperatures, but also we can have it in visible light and ultraviolet, which, unlike conduction and convection, can transport heat through a vacuum. Okay, then the first two methods, they need a medium. For the third method, we don't need that okay, we don't need the I would say the medium. Objects that are hot enough will glow, first red, then yellow, white, and blue, and objects at body temperature radiate in the infrared and can be seen with night vision. Like, we have like many methods now of detecting infrared, and you can see like these thermometers that we have been using during the corona. The energy radiated has been found to be proportional to the fourth power of the temperature. Okay, then this is really P the power Q, energy divided by time. The constant here, sigma, is called Stephan-Boltzmann constant, and it is given. And the emissivity, it is a number between 0 and 1 characterizing the surface. Okay? Black objects have emissivity of near 1, while shiny ones near 0. Now, here we are talking about two rooms, each a cube, 4 meters per side, share a 12 centimeter thick brick wall because of a number of 100 watts light bulbs in one room. It's too many, okay? The air is at 30 degrees Celsius, while in the other room it is at 10 degrees Celsius. How many 100 bulbs are needed to maintain the temperature difference across the wall? Here we can use the equation first for conduction, and we can get the power from that, and we can find for the number of bulbs. We can actually divide by 100 watt for each bulb, and then it's going to be 22.4 bulbs. Okay, an athlete is sitting underclothed in a local room whose dark walls are at a temperature of 15 degrees Celsius. Estimate the rate of heat lost by radiation, assuming a skin temperature of 34 degrees Celsius and E to be 0.7. Take the surface area of the body not in contact with the chair to be 1.5 meters squared. Okay, all these are really ready numbers to put in the equation. This is E, this is Boltzmann, this is E, this is Boltzmann constant, this is the area, and that is T1, and this is T2. Of course, it is to the power 4. Now, using the solar constant, estimate the rate at which the whole Earth receives energy from the sun. The solar constant, it is 1350 watts per square meter. We're going to assume that the Earth, it is radiating an equal amount back into space, which means it is really the equilibrium. Then, assuming the Earth is a perfect emitter, as E equals 1, estimate the average surface temperature. Okay, first we will find the power, which is delta Q over delta T. We have E sigma A T squared. And I will say this is going to be A times the solar constant. And from that, I can calculate delta Q over delta T. And I will put this equal to the equation again to find what is really the temperature. Because this is my major equation here. And this is really the summary of this chapter. Okay, if you have any questions, please don't hesitate to email me. Thank you. Bye.